doctor, so.
That might play for the rest. Yeah. No, let's chat after class. Yeah. All right. So we are back after a week off. Everyone looks about as tired as when we left. So I don't know what you guys were up to over the whole week, the week break there, but hopefully you guys did find a little bit of time off to kind of catch up on things and maybe even find that last little bit of energy there to push through. Because what do we have? 11 classes left, I think, right? So, all right, we got the 2 this week, and then we've got the 3, basically 3 weeks up until the end here. So not too much more. We've got about 2.5-ish or so chapters left to go through, so we're looks like we'll be just fine with getting everything finished. With maybe even a little bit of time at the end to see if we can do some review days or something like that. But we don't have to particularly rush through anything. That's what it is. I mean, any more so than we normally have to rush through things, I suppose. But anyway, next week though, we do have our next exam, right? Yeah, that's right. Not enough wailing yet, so I'm going to work on the gnashing of teeth and all that as we go through the rest of this week.
I'll work on the gnashing of teeth because I prefer to not damage mine.
Right, but the good news is, right, we don't have too much on this upcoming exam, and it's I always hesitate to say these kind of things because it's my opinion, right, but it is one of the easier exams of the semester, right? Because we basically only have about 2-ish or so chapters that will show up on there. Remember, we have the tail end of the equilibrium chapter there, right? Basically, remember, we ended with buffers. And then we had the solubility part of, what chapter was that? 17, yeah. The equilibrium, the solubility part of chapter 17 there, which had the common ion effects and how do we calculate solubility and whether we can, or how do we predict whether things are going to dissolve or precipitate out, right? So we had that tail end of the equilibrium part there. And then we went through the thermodynamics. Well, the second thermodynamics chapter there, where we dealt with delta G, and we talked about a couple different ways of what delta G tells us, and that ended up being a fairly qualitative chapter, right? There wasn't too much in terms of calculations that we needed to do with it. So that's a good conceptual chapter to make sure that you can kind of understand what delta G tells us and the let's say the different reactions that we can apply the concepts of free energy to, right? How can we know if a reaction is spontaneous or not? That's the kind of stuff that came out of there, right? And then we'll have a little bit of the stuff that we have from electrochemistry here. I'm not we have the exam next week, and so I'm not a huge fan of, giving you guys a lecture on Monday and then that stuff is on Tuesday. So we'll cut off the material and wherever we get to by Friday is what it is, right? And so I'll make a distinctive post, I guess, on what section we kind of ended with in chapter 20 here, right? So the tail end of chapter 17, and then we went through 19, and then we'll see how far we kind of get here in chapter 20. Okay. So we've got that exam, and then we'll finish up chapter 20 and move into the organic chemistry / inorganic chapter there, and then it's final exam time, right?
Aren't those very different things?
What?
Organic and inorganic chemistry?
Kind of. I mean, but it's one of those things where everything in chemistry is related, right? So everything kind of comes back to some of these core principles, and that's one of the ideas of what general chemistry as a class is supposed to be. All right, it's supposed to teach you guys the general parts of chemistry, right? So I think you guys figured that part out. you guys understand that, right? So that's kind of why we touch on all the different subjects here and there. And then as you guys get into these more advanced classes, you start to focus in a little bit more on, how exactly does equilibrium affect, the chemistry of biology, right? And so that's where we get into biochemistry and chemical biology and those kind of things, right? So you guys get into those detailed parts there, okay? You got a question?
Well, I'm gonna say the exam is
I mean, that's gonna be on everything.
Yeah.
So I'm gonna take every question you guys missed on the exams and put it back on there, right? And you're like, that's great news. Why? Because if you missed it once, you're not gonna miss it again, right? The oozing confidence of the crowd here. Yeah, the final exam's cumulative, right? But this upcoming exam is, I mean, equilibrium, right? If calculating solubility constants is based off of your understanding of equilibrium, right? So you have to understand in chapter 16 and 17 that we went through there, but it's not like I'm going to be asking you a buffer question, so to speak, on there, okay? Does that make sense? Okay. Cool. So we good? You guys have the plan? You guys have lab this week, yes?
No.
No. Okay, good. So you guys got nothing but free time to study. Yeah. Study physics and what else? Calculus. Oh, just physics. Okay. All right. But anyway, so chapter 20 here, we're getting into electrochemistry, and again, this kind of fits into, if you guys remember me telling you at the beginning of chapter 19, the next 2 or 3, well, yeah, really 3 chapters here are kind of different specialized topics. There'll be a little bit of overlap with some of the previous stuff that we did, and we'll see where electrochemistry ties into thermodynamics and gives free energy a little bit here, but it's one of these kind of separate topics that is, I guess, one of these core principles of how things work, right? Electrochemistry is going to be important, again, when you guys get into biochemistry and you talk about cell potentials and things like this. And so you guys will see these ideas come back up again in about 2 or 3 years, just depending on how long it takes you guys or where you guys are in terms of getting to biochemistry and that kind of stuff. So you'll see this come up again, although we don't really talk about it too much in organic chemistry, and so it will kind of be after that when we get to the bio-inorganic or the biochemistry part of things. Right? So, but we just have a couple of equations to learn in here. We have a couple of topics such as balancing reactions. And you're like, well, I remember all that already. I mean, that's good, but we have a different way that we have to balance reactions in here, and we'll talk about that. Right? But one of the core ideas that we'll get to first is oxidation states. And so that's one of these things that we learned about in the first semester of general chemistry. And that's going to be a core idea that we have to use to be able to answer some of the questions that come out of this chapter. So I'm not going to spend too much time on it here because my assumption is that you guys remember everything from Gen Chem 1. Again, the oozing confidence of the crowd. All right. The point being, make sure that you go back and review some of these oxidation state things. Okay. Like I said, I'll jog the memory here a little bit, but it's one of those things where make sure we do a little bit of practice to kind of bring back the tool set or the skill set that we need to be able to assess oxidation state for different elements and molecules. Okay, so that's going to be one of these core ideas that we're going to come back to. Okay? And then we have a couple of equations towards the tail end of this chapter that's going to involve paying very close attention to units of things. Okay, and I'll walk you guys through an example of what I mean with that. Right, we can calculate how many electrons are transferred, and we can calculate the mass of things that are added or removed as we do some electroplating or redox chemistry here. Right. So we'll talk about these different concepts, but it's going to be really important to pay attention to the units of the information that's given. Okay? Yeah?
Did you remember to start the...
Yeah, I'm pretty sure I did. Right? Is that...
Yeah.
Okay, cool. All right, cool. But before we get to that, let's get started with prayer, and then we'll start to knock the rust off of redox reactions here. But Lord, we just thank you once again. We just thank you again for a new season here, Lord. We know that Easter is something that we celebrate once a year, Lord, but we just pray that you keep that on our hearts, Lord. Just help us remember the sacrifice that you made and then the promise that you kept for rising again, Lord. And we just thank you for that blessing, that gift that you've given us freely, Lord. And we pray for the people around us who don't know you and haven't accepted you, Lord. We pray that we can be your vessel to show them who you are to us and the things that you've done in our lives, Lord, and just the blessing that you are to us each day. So just give those opportunities just to share with those around us. And just give us the words and give us the strength and the courage just to step out in faith and to be able to proclaim you loudly and proudly, Lord. And we just pray all this in your name. Amen. All right. So, electrochemistry. All right. Now, this is modern, in modern context, I guess, one of the most important areas of research that's currently being done, right? Because I believe, let's see, looking on the desks, right? I can see pretty much everybody in the classroom here either has their phone or a laptop, and right, all that stuff runs off of battery power, right? And that's the most common types of batteries that we have today, right? These lithium-ion, well, I think, I'm pretty sure it is, at least the stuff in electronics, the lithium-ion batteries there, right? And so basically what we're going to talk about in this chapter is just how can we move electrons from one part to another part of a battery, is what it is, okay? And we'll talk about how many electrons are moved and the voltage that's associated with that. That'll be some of the things that we calculate with this. And we'll talk about why, in broad terms, do we have certain elements that can make a battery, and why do we have certain elements that can't make a battery, right? So we'll see that a little bit here, but you know, this is one of these. If you go into the research field for materials, building a better battery is high priority, right? Especially if we ever want to move away from the fossil fuels, right? I'm not making some giant argument here. It's just like if we want to move away from fossil fuels to some other alternate source, especially solar energy, we got this problem that's called night, right? So if we're working on solar power, guess what you can't produce at night? Solar power, right? So we have to have some way of storing energy overnight, and the best way we have of doing it at the moment are these things called batteries, okay? But we've got a problem. And the problem is, imagine, right, or when do you use most of the energy? At night when you're at home, right? You have the lights on, you got the TV on, but you're cooking dinner, right? So we have to have a lot of energy stored up somehow to be able to, you know, meet the requirements that our modern society has with that, right? So you either build a whole separate house to store all the batteries that you need, right? Or we come up with a better battery or a different system is what it comes down to, right? What's up?
Are we gonna discuss the infamous Baghdad battery?
No. I'm not sure I know what that is, but.
It's like the first battery ever.
Oh, that thing with like the, yeah, where they found
The
a piece of
orange
metal.
juice and the can.
Yeah. No. All right, so what in the world is electrochemistry? You know, I'm never really going to ask you a definition of things, right? But just to put things in context, right? The study and use of electron flow in chemical reactions. Great. Now, why is this important? Well, we talked about redox reactions in the first semester. And we said this was a type of reaction that we end up seeing, right? Where electrons are moved from one metal or one element or one atom to another, okay? Now, we have to kind of learn to separate this in our brain or in our own definitions or wordings, that all chemistry involves the movement of electrons, okay? As you make or as you break bonds, you guys are moving electrons between atoms, right, to bond a carbon and a hydrogen, for instance, right? We're making that bond or we're breaking that bond between the carbon and hydrogen, okay? But the difference here with a redox reaction is we're transferring electrons from one element to another, okay? So it's not necessarily that we're making or breaking bonds, it's that we're seeing a change in the amount of electrons that are around a specific element or not. That's what the difference is. And the way we kind of contextualize this in the first semester is that not every reaction is a redox reaction. And we proved that with a couple of examples of these kind of things, right? So just keep that in mind, right? But there's your definition for that, right? And if we can move electrons or generate electrons, right, we can use that to form a battery, right? Corrosion or rusting or whatever you want to say with that is a redox process, right? It's an electrochemical reaction. If we apply electron flow, right, we can drive a reactant favored towards products there. And what this kind of means is there's actually a branch of chemistry where we can use current or voltage or potential to drive reactions in different ways. So if you want to think about this in a certain aspect, when you guys go to the lab and you guys mix two chemicals together, you heat it up and you stir it up and you hope that a reaction happens. Well, adding a voltage or a potential is another way that we can kind of drive a reaction in a specific direction. And so what this means, again, if we're speaking in broad terms, is if I add electrons, okay, if I add electrons to one side of my reaction, It's almost like Le Chatelier's principle, right? If I add electrons to one side, that's basically a reactant, which is going to shift the equilibrium to the other side, is what it is, okay? So much like what we talked about when you have an exothermic or endothermic reaction, remember we added heat as one of our components to our balanced equation, right? And then if I added more heat, it shifted the equilibrium, right? Or if I removed heat, it shifted the equilibrium there, okay? So adding electrons is another, let's say, component that we can think about on how to move the equilibrium or which side is favored in a reaction. Does that make sense? You guys follow along with this? Right? It's just something else that's in there, right? Okay. All right, so here we go. So this, I believe, is almost the, or it might be the exact same slide that I gave you guys in the first semester here. So if we're going to look, right, if we're going to look at the transfer of electrons in a redox reaction, guess what we have to be able to figure out?
Oxidation number.
Where the electrons are, right? Because if I'm saying, hey, 2 electrons move from this to this. Okay, furiously take notes. All right, good, right? Zinc moves to electrons. Well, how do you know, right? And this is what our oxidation states or oxidation numbers tell us, okay? They're a way of us figuring out or calculating or qualitatively assessing where electrons come from and where they move to, okay? You guys with me on this? So one of the first things you have to do when you're assessing a redox reaction is saying, hey, what are the oxidation states and things that are involved, okay? And so you have to go through your checklist here. We have to sign oxidation states, these kind of things. Okay. Let's say rule that's missing here, which I always like to add in, is this idea that your group 1A and your group 2A metals are going to be +1 and +2 respectively. Okay. Here's what we have to think about. If I'm assigning oxidation states, okay, if I'm assigning oxidation states, I have to look for known oxidation states, right? So if I see fluorine as part of a molecule, it's pretty much always going to be -1. Okay? How do we know that? Well, I'm telling you, there's no exceptions. The only exception being the top point up there, right? If we have fluorine as in its pure elemental form, anything in its pure elemental form has a 0 oxidation state. Okay. So if I have something like sodium fluoride, NaF, right? My assumption is that fluoride has a -1 charge. There's really no exceptions to that. So that's a known oxidation state that I can assign. And then I can move forward from there and make my assessment on where electrons come from and where they go to. To assess an unknown, I have to know an known. That's all I'm saying. Okay? And this table tells us our knowns. Okay? The other halogens, chlorine, bromine, iodine, pretty much always have a -1 charge. The only difference is when they're bound to themselves. Okay? So if we have an odd chlorine bromine species here, then we have to assess which has a higher electronegativity, right? And then we can make our assessment based off of that. Okay? Hydrogen is always good. It's always going to be a +1, with the only exception being metal hydrides. Those are kind of rare beasts. Oxygen is always very important, pretty much always going to be -2. The exception being if we have peroxides or halogen oxides. So there's a couple of random examples here, or exceptions here and there, right? And you can add to this list your group 1A and your group 2A metals, right? Sodium, or I should say lithium, sodium, potassium, right? These things are always going to be +1. Unless they are in the elemental form, right? And magnesium, calcium, right? These kind of things are always going to be +2, unless they are in their elemental form, right? So these are our knowns that we use to assess our unknowns. Okay? What's up?
What's a metal hydride and what does it do?
They do lots. But what are you asking?
Like, what would an example of a metal hydride be? Would it be like...
Sodium hydride, NaH.
Okay, so it would just be one hydrogen bonded to a metal?
Yeah.
And then what's the application for those?
Lots. I'm not trying to purposely be coy about this. There really are a lot of examples and uses for those. They're powerful reducing agents, right? Which we'll talk about a little bit later. That's probably their most broad description of their application. They're powerful reducing agents, but they're also So I guess in a modern context here, what's the word I'm looking for? The hydrogen economy, right? People are talking about storing and using hydrogen as an energy source.
Right.
Well, part of the problem with using hydrogen as an energy source is it's a gas, right? You know, liquids we can deal with, right? They're relatively easy to handle, but when you have a gas, they have this nasty habit of escaping, right? But one method that we have of trapping hydrogen is that we actually bind it to a metal and we form metal hydrides. And then you can pass a voltage or a current through there to reduce it, to oxidize it back to hydrogen gas, and then it gets released. So we kind of passively store hydrogen in its hydride form rather than in its gaseous form, right? So it makes it a little bit different, right? That's just a couple of the stuff. But you'll learn a lot more about that. You know, organic things. Okay.
So would that potentially be an answer to the whole battery problem, to just have like a large amount, like a storage container of metal hydride?
Sure.
Just be like.
Yep. Now the question is, what metal is best at it? Because not only do you have to store it as a hydride, you have to make it reversible too, right?
So you need to be able to collect that metal and then repeat the process and like.
Yeah. And it needs to be essentially infinitely repeatable, right? Because if you have this in your car, right, you don't want your car to you know, okay, it's been 6 months, it's time to swap out your, you know, your hydride source, right? There's another couple $1,000s to do that, right? These kind of things. So you have to bind it, reverse it, you know, make it last a long time, make it robust, make it work at ambient conditions, you know, all these kind of things, right? We have to get more energy out than what we put in also. Right? And you're right, there are people who are looking at this stuff. Okay? But at the moment, I don't think we have a great answer for it either, is what it is. But there you go. Now you guys know how you can just skip straight to retirement, right? Just solve the hydrogen problem, right? And you guys can retire by the time you're 32 or whatever, right? It'll be great. No takers, huh? All right, fine.
I mean, it sounds like a great plan, I just don't actually think I'm smart enough to do something.
Well, let's see if we can give you the basics to figure it out, right? Boy, am I good at this. All right, so here's the basics of a redox reaction, right? So we have the reduction and we have the oxidation. Now, if you remember, some of the terminology that came out of, again, this stuff in the first semester is we talked about something getting reduced, something getting oxidized. We talked about reducing agents, we talked about oxidizing agents, right? And so we're just going to kind of review those different terminologies here and just kind of, again, knock the rust off here, right? So a reduction is a gain of electrons, right? So we decrease an oxidation number. Okay, so if I'm gaining electrons, I am adding negative to myself, right? That's what adding an electron does, right? We make ourselves more negative, okay? The opposite of that is the loss of electrons. If I'm losing electrons, I become more positive. So be careful, because this is one of these first parts where we can see some confusion come in, right? After we assign our oxidation numbers, we have to ask the question, am I adding electrons or removing electrons? Am I becoming more negative or am I becoming more positive? Right? So that's one of these assessments that we have to make. And after you assess that, right, then we can say what is being reduced and what is being oxidized. This is going to be important because where we're moving to is I'm going to ask you the question of, or ask you to build a battery, okay? And there's two parts to a battery, or two main parts. One part is called the cathode and one is called the anode. And at one of these, we'll talk about it, right? At one of these, something gets oxidized, and at the other, it gets reduced. So if I'm asking you to build something, right, you have to make sure you put the right thing at either the cathode or the anode. And I'll tell, have you guys ever tried to jump a battery in a car, right? You guys ever done that? So, I'm a dum-dum sometimes, and I remember I was trying to, somebody's car broke, I didn't know them, which is great, you'll see why at the end of the story, right? I didn't know them, right, their car had broken down, like, oh, okay, I got jumper cables, pull my car out, get everything hooked up, and I accidentally crossed the wires.
No!
Right? Have you guys ever done this?
Oh!
It makes a fantastic spark of showers. Now, I didn't know this person, and so as soon as I do that to their nice car, right, they think I'm a complete moron, right? Right? And so, but this is what we're talking about. If you mix the wrong things together, you have maybe the unexpected outcome of showering sparks all over somebody else's car. It wasn't, my car, what do I care, right? So,
Is
no,
your car attached?
yeah, but that's no big deal, who cares, right? So, no, it's fine. But anyway, right, so two parts here, make sure you guys don't cross the wires whenever you guys do this, right? And you have to know what is getting reduced and what is getting oxidized, okay? Just like your car battery has a cathode and an anode, a positive and a negative end, right? If you cross these two up, you're gonna, have some problems because electrons are gonna want to flow, not in the direction that we maybe intended them to, is what it is, okay? So it's very important to make sure that we understand exactly what's getting reduced and oxidized. And the only way to answer that is through assigning their oxidation numbers, okay? So step number one, when you guys are assessing a redox reaction, is make sure that you guys can assign the proper oxidation states or oxidation numbers to each of the molecules, excuse me, to each of the molecules that are part of the reaction then, okay? Okay, so yeah.
Are we gonna get to electroplate something in lab?
Maybe, I don't know. Probably not in the way that you guys are thinking. The most common experiments that you guys do is you guys like build your own batteries, right? And you measure the different potentials based off of concentrations and things like that.
That's pretty
Right.
interesting.
So I mean, you're electroplating, but maybe not in the way that you're, that you might think of like, oh, I gotta, plate this with nickel, that kind of thing.
I knew a priest that used to plate iPhones with gold and sell them to make enough money to buy the church a new monstrance.
A new what?
Monstrance.
But you had gold.
I don't know what a monstrance is.
It's the thing that looks like a sun that you put the consecrated.
Oh, that's
crystals
okay.
in.
Gotcha. Gotcha.
Yeah.
You think the church would pony up for that kind of stuff, right? But maybe. Why didn't you just make one, electroplate it himself? But sorry. So anyway, if we have the oxidation states here, right? So magnesium is in its elemental form. Anything in its elemental form has to have an oxidation state of 0, right? Remember, one of the rules that's on the previous slide there, if you guys want to look back, is that the sum of the oxidation states has to equal the charge of the molecule. Okay, so if we have a neutral molecule, everything has to add up to be equal to 0. Got it? So how many things are here? Well, there's just one magnesium, and it's a neutral molecule, so then magnesium has to be equal to 0. Got it? Now, magnesium's a group 2A metal, you tell me, right?
Yes.
Yes, thank you, right? And when it's bound to something else, then it will have a +2 charge. But in its elemental form, right, it's going to have a 0 oxidation state. Yeah, what's up?
And what does that oxidation state reflect again?
Just what's a good way of putting this? Where are the electrons hanging out, right? Might be a way of
Potential?
thinking.
Like,
Hmm?
is it a potential, is that something to do with potential?
Yes, when you put two things together, right, when a redox reaction happens, we'll see a movement of electrons, and we can measure that as potential, yes. The tricky part with this stuff is, we also talk about formal charges, right? And that's another way we have of assessing where the electrons are hanging out, right? But there's they give us specific information for when we need to answer different questions, is what I would say with that.
Okay.
Right? There's separate ideas, but they're kind of based off of the same principles also, right? So if we have HCl over there, if we go back and look at our rules, right? Our rules tell us two things. One, that hydrogen is always going to be a +1 charge, with the exception of what? If we have metal hydrides, right? Well, we have H bound to Cl. Is Cl a metal?
No.
No, right? So we don't have to worry about metal hydrides. If we had something like sodium or potassium, right? Then we'd have to consider the, whether we have a metal hydride or not. But, right, chlorine is a non-metal, right? Remember our classification on the periodic tables there, right? So it's a non-metal. And on our list of rules, it also tells us that chlorine typically has a -1 charge also, right? So we're just using our rules to figure out what the oxidation states are here, okay? So we assess one side, we assess the other. H2 is the elemental form of hydrogen. Okay? It's one of our 7 diatomics, right? Hydrogen, nitrogen, oxygen, fluorine, bromine, iodine, right? There are 7 diatomics that are the elemental forms. That's important to recognize when you're going through and doing your oxidation states. If those are our 7 diatomics, what's everything else on the periodic table?
Monatomic.
Monoatomic, right? There are a couple exceptions here and there, sulfur being one of them, mercury sometimes being another, okay? But most everything else is a monoatomic. So if you just see magnesium by itself, or sodium by itself, right, or iron by itself, and we assume that that's its elemental form, and that its oxidation state is always going to be equal to 0. It's going to be important to recognize the elemental form of metals, because that's where we're going to spend most of our time discussing how to make a battery, okay? So, monoatomic metals, elemental form, oxidation state is 0, okay? In this case, though, we have a diatomic 0, magnesium, our group 2A metal, always +2, chlorine, 2 of them -1 each. Right? Remember, when you're assigning oxidation state, you want to look at individual atoms. Got it? Each chlorine in there has a -1 charge. And there's 2 of them, so overall a -2. Okay? It's important because we're going to have to look at it on a per atom basis. What changes with each individual atom here, right? But anyway, as we look at this, right, we have hydrogen going from +1 to 0. That means we have to add an electron, right, to each of the hydrogens. Because if I have a +1 and I add an electron, I get to 0. This is tough math, Dr. H. We had a week off, right?
Yeah.
But is everybody with me on this? And this is where the tricky part comes in. I'm adding a negative, right? That means I'm adding an electron, right? Which means what? If I'm gaining an electron, that means the hydrogen is what? Reduced. Got it? Right? It's a gain of an electron. That's a reduction. I'm adding a negative, or I'm removing a negative. Okay? So we have our, and we can go through and make that assessment here also at the bottom there, right? The hydrogen, the H+, right, is reduced, the magnesium is oxidized. Okay? I just had a thought that I wanted to share. I just slipped my mind here. What was it? Oh, that's what it was. So now if we think about this, right? The other important thing, and we're going to bring this in the next couple of slides here, is electrons are part of molecules. Again, I can tell that, that if you guys are shocked by my statement of this, okay? If we balance a reaction, guess what else we're balancing? How many electrons there are. Got it? So if I have 2 H+, right? I have 2 hydrogens here. I have to transfer 2 electrons to do that. So electrons have to be balanced also. And that's going to be one of these important ideas that we're going to bring up here. One of the first big topics that we hit in this chapter is how do we balance redox reactions under acidic or basic conditions, okay? So it's going to be important to kind of pay attention to where the electrons are and how many there are and what's part of the redox reaction and these kind of things. Got it? Cool. Okay, so here's some good, let's say, pseudo practice for you guys, since you already have all the answers. All right, to give the oxidation numbers for each atom, identifying the oxidizing and reducing agent. Okay, so we could go through and we could walk through this here, but something important. So we define oxidizing and reducing. Well, what does it mean to be an oxidizing or reducing agent? Okay, yeah.
If you're an oxidizing agent, you get reduced, and if you're a reducing agent, you get oxidized.
So say half of that for me. Say the first part of that.
If you're an oxidizing agent, you get reduced.
If you're an oxidizing agent, you get reduced. Yes, correct. Okay. What does it mean to be an agent, though? Right? Well, we're not talking about the let's make James Bond jokes or whatever we want to here, right? But you're causing something to happen. So reducing agent causes a reduction to happen. It itself gets oxidized. You guys with me on this? If you're reducing agent, you're causing a reduction to happen in something else. What's a reduction? A reduction is a gain of electron. So if I'm causing something else to gain electrons, what happens to me? I have to lose those electrons. Got it? So if I am a make students richer agent, if I hand Andrew $5, right? I am now the agent causing his monetary success. $7. I think that's what I got, right? You guys with me on this? I am causing him to become richer, but I myself have to lose that. Okay, so I am the agent that causes this to happen. And this is another point of confusion, okay? Because we talk about reducing, we talk about oxidizing, then we talk about reducing agent and oxidizing agent. But like RJ said there, right? These are the opposites. A reducing agent gets oxidized. Right?
Oh, no.
That's gonna be a thing now.
Don't you dare. Don't you dare.
Sorry, did I misspeak on something?
Chris, you shut up too.
Okay, anyway.
Pulling up
RC.
Oh, RC, sorry, I'm sorry. Sorry. My bad. I didn't write that. My bad.
You're good, Doc. It's just we're all so brain dead at this point.
Yeah, I'm with you on that one. All right. Anyway, sorry about that. So, but if we have well, I guess let me back up here for a second. So how do I keep all this stuff in my brain here, right? So I kind of keep one statement, and it's a little bit easier for me just because of where I went to school and these kind of things, and that's not too important. But here's kind of what I always keep in my head here, okay? So I went to school in a place called Raleigh, North Carolina, which is basically spelled just like that with an H at the end there, so a little bit easier. So what this actually means for me is reducing agents lose electrons, right? That's RALE, right? It gets oxidized, okay? Now why do I prefer to remember this kind of stuff instead of the Leo says grr and all these other things, and oil rig and all that? Because this tells me everything I need to know in one statement. It tells me if I'm a reducing agent, I lose electrons, and if I lose electrons, that means I'm oxidized. Got it? So if you remember that one thing, then you can kind of remember everything you need to there, right?
But oil rig is more fun.
Yeah, I mean, I'm not telling you what you have to do, I'm just saying this is what I do, right? And because I do it, that means it's objectively better than everything else, right? That's the way the world works. What's up?
How would you recommend like memorizing certain the oxidation rules? Like a
Practice. That's really what it comes down to. Yeah, just work through some of the examples. Literally, you can flip open to probably any page in the textbook, and it'll have some kind of molecule there, and just assign the oxidation numbers to it, right?
Can you repeat?
Of course. So RALEIGO, so reducing agents lose electrons, right? It gets oxidized. And I'll have another stupid saying for you guys later on in this chapter too, right? So, good? So now that we have everything that we need to know about oxidizing agents and reducing agents, right? And how to assign oxidation states and tell whether something gets transferred electrons and all these kind of things, right? So now we need to pull this stuff together and see how we can address the new stuff that we're going to learn in terms of how we can start to build a battery from these things. What's up?
How would you pronounce that?
How would you pronounce that?
I'm interested in how you would pronounce it.
Raleigh goat?
Constant
Yeah.
right?
I can tell I shocked everyone with that. I thought it had a J in there. Right? Just kidding. Raleigh Joe, because it's French, all right? I don't know, I can't speak French. So.
I think Raleigh actually knows. Well, is it French? Okay, now I have to Google that.
So Walter Raleigh, is that what you think that is? All right, so if we kind of put these two ideas together here, right? How can we start to build a battery, or how can we look at these things, or what do we need to address, or where do all these ideas come together, or where do all of these things come together? So what we're going to introduce, or one of the first new topics, is this idea of a half reaction. And a half reaction is exactly what it sounds like. So guess what it is? It's half of a reaction. Got it? So, but specifically within context, it's going to tell us, right, the number of electrons, broadly speaking here, it's one of the things it's going to tell us, how many electrons get gained or lost in a specific step, okay? So for instance, if we have the overall reaction here where we have solid zinc reacting with copper in an aqueous solution, okay? What we'll see happening is that zinc will turn into its 2 plus and copper solid, will form, okay? And so if we take half of that reaction, aka what happens to the zinc, right, or what happens to the copper, we can see then, and what we are looking at is what happens with the electrons that are transferred in between there. You guys follow along with this, right? It's not that complex at the moment, right? But you guys see what I'm saying? There's two separate parts what happens to the individual metals as part of this reaction. Good? Why is that important? Who cares about half reactions? What's the important part, or one of the important parts of looking at these half reactions? It's something I just mentioned a couple minutes ago. What has to be balanced?
The electrons.
The stoichiometry and the electrons as part of this, got it? Right, so if we take a look at the half reaction, it'll tell us how many electrons are required for each half of a reaction. If we know what each half of the reaction needs in terms of electrons, guess what it's easy to do? Balance those equations, got it? If one needs 3 electrons and the other needs 2, then we can figure out how much has to get, the stoichiometry of each part that's in there, right? What's up?
How come you can't tell, how come you can't do that by you looking at the full reaction?
Well, you can, but I'm just saying this is another way of doing that, specifically when we're building batteries and these kind of things.
Okay.
As we go through a couple of the examples, it'll become a little bit more obvious with that too. That's not the only information that comes out of half reaction, or the half reactions.
Okay.
The other thing that we'll talk about just a little bit is the voltages that come out of this too. Because we'll see in some cases, right, maybe to answer your question before we get to it, in some cases, metals can transfer 1 electron or 2 electrons. And then those have different voltages associated with it also, right? Cool, okay. So here's that point, right? If we have aluminum and zinc coming together, right? Aluminum in its half reaction form, right? We can, well, let me ask you guys a question here. So what's happening to aluminum there on the top? Aluminum solid turns into aluminum 3 plus ion and 3 electrons. What's happening to the aluminum solid?
Bonds of things.
It's getting oxidized, right? It's losing those electrons, got it? Okay, if it loses those 3 electrons, where do they end up going? To the zinc, but be specific. The zinc,
Gets reduced?
it's true. Be careful, zinc is not the same as zinc 2 plus, right? Zinc 2 plus is a zinc ion. Got it? Right, so this here is going to pick up some electrons. Does that make sense?
Mm-hmm.
Why does that make sense?
Cause math?
Give me a better reason.
Positive?
It's positive, got it? What charge do electrons have? Negative. What are they on the hunt for?
Positive?
Something positive, got it? So when you guys are adding electrons to things, right, usually there's something positive that they're going to get added to. Is it always going to be so evident as this? Mostly, yeah, right? Okay. Now sometimes you have to go through and assess oxidation states and electronegativities and these kind of other stuff as we get a little bit more complex, right? But if I'm something negative, I'm always going to be looking for something positive, okay? And I'm going to be on the hunt for something that is the most positive I can find, okay? You guys with me on this one?
What if you're naturally cynical?
Huh?
What if you're naturally cynical?
Then you're always negative, right? And you just repel everything around you. So, it's a good lesson in life, right? So, if we know the half reactions here, okay, aluminum loses 3 electrons, zinc needs 2 electrons. So I can easily, right, go through and balance my reaction, right, just based off of looking at how many electrons get transferred in each case. That's all it is, right? Does this seem that complex at the moment? No, not really, right? Could we also just go through and assess the charges, the 3 plus and the 2 plus, and balance those? Yeah, right? Because if you notice, right, over here we have a total of 6 plus, and here we have a total of 6 plus. Got it? So make sure you always go back, and that's going to be useful, right? Why is it always useful to have 2 ways of checking something? Because once you have an answer, what's the most important thing you can do? Go back and check it, right? So if you're not just counting electrons, we can also go through and count the charges. And then you have two ways of making sure you didn't do a typo or a clerical issue or something like that, right? It's almost as if I'm telling you points to be careful with when you guys are going through and answering questions. Okay, so there's how we can, or one way that we can apply our half reactions. Okay, so now we get into, I think this takes up like 4 pages. This one of the, not this exact problem, but a similar problem takes up about 2 or 3 pages in the textbook itself as they walk you guys through it. Okay, so let's say that we have to balance this reaction here at the bottom, okay? There's a certain number of, or there's a certain series of steps that we're going to have to do to be able to balance that redox reaction. And the first thing we have to assess is whether it's in acidic or basic solutions, okay?
Wait, what does that have to do with it?
What does what have to do with it?
Oh, never mind, I see.
Right? So we have to be able to, the first assessment is whether we're under acidic or basic conditions. The reason why we have to ask that question first is because we have to answer the question of what else is present in solution, okay? So, question. I am an acidic solution. What's present?
Hydrogen, proton.
Protons, H plus. What else is present?
The thing
Water.
that's attached.
Right? So H plus and water are present. Got it? If I'm a basic solution, what's present?
OH.
Water and OH minus. Got it? So we have to be careful of what is present in solution because that's going to change how we go through and address our answer at the end. Okay? Whether I have H pluses or OH minuses, but we always have water around also. Okay? Now the book is going to walk you guys through this in a slightly different manner than the way I do. Guess which way is correct?
Yours.
Both, right? I didn't say which way is better. That's obvious. So guess what, right? Both of them are going to get you to the same answer. Okay? Now what we're going to do, I think mine takes like 5 or 6 steps, I forget off the top of my head, right? This is just like your buffers, okay? You guys remember, I hope, I gave you guys a big warning about buffers, like, hey, these are complex. You gotta go through, you gotta work this, you gotta figure out the steps, you gotta practice it, you gotta, I'm telling you the same thing here, okay? These are some complex steps. They're not difficult, it's just we have to make sure that we're doing it in the right order, right? But we have to go through, work the steps to get to the right answer each time, otherwise we end up making mistakes. And then when we make mistakes, we lose points, and we don't want that. I don't want that. As I've always told you guys, the easiest thing for me to grade is a perfect exam, right? I can just go through 100 and I'm happy, okay? Otherwise, I'm okay, how much partial credit, right, you know? And then when I'm in a bad mood, it's even worse. I'm just kidding. I think, all right. I hope. I try and remain impartial, okay. So we're gonna have a couple of steps to go through this stuff here, right? Okay, so step 1, what is oxidized and what is reduced? Okay, one of the most important questions to start everything out with. Okay. How do we answer part 1 there?
We look at the equation,
And
figure out
Sign.
what loses the gain electrons,
how?
oxidation charges.
Looking at our oxidation states. Got it? So see what you guys come up with. Hmm?
Is acetone a transition metal?
That's arsenic. It's below phosphorus. AT is that.
What's arsenic?
Well, that's my favorite too.
I
Oh.
don't,
You don't have a tablet that can access the
Yeah.
internet,
Oh.
or a phone that can access the
Oh,
internet.
lost in sauce.
like,
Okay.
Or you don't have a periodic table app.
there's a periodic table app.
There's a billion of them. Yeah. Wait a minute, I can pull up more than cat pictures on this thing. Oh. Suspicious. Mm-hmm. Is it? Okay, well, you're making a lot of assumptions since you haven't assigned the oxidation states over here. Well, you have to assign it to everything that's in there, right?
Alright, I'm doing a great job of confusing myself here.
Good. Wake up in the morning, stretch, have some breakfast, and then get confused. So, -8 and a -3 is balanced out by a +3, so we can.
Yeah, that's what I'm confused about.
Mm-hmm.
What the heck is going on?
Yep. Yeah, okay, just make, double check for this. Cool.
I was so lost. I was looking at A is one, S is the other. Like, why
Ah.
is S small? Is that S?
Yeah, just one of those elements that we don't talk about too much, right, so.
Oh boy.
Oh, there, sorry, let's see. What is this, that page? No, okay, so good question, right, so it's what individual atom, right? So hydrogen starts at +1, right, starts at +1 and stays at 1. But what changes as part of this? Where are these numbers coming from? Or where did you get this from, I guess? Oh, okay. So remember, it's on a per atom, right? So you have to take a look at H here, arsenic here, oxygen here.
You're trying to get quad.
Iodine here, and
Yeah.
hydrogen here, and
That's all you
right? So
Quad
each
is nuts.
individual part of this. has
Quad's
to be
two and
assigned.
itself into
So we
it.
do for each.
Oh, yeah, yeah. Oh.
Yeah, that's what I have right now.
Or another-
Next year, I'd like the same thing.
Yeah.
Think about rooming.
Yeah.
But then behind information.
Cross-country runners.
That's the question, right? So now we're assigning oxidation states, now we need to take a look at what changes and what stays the same. Something's gonna become
I know.
more negative and something's gonna become more positive. And there we can assign what's reduced and
R,
what's
yeah,
not.
it's an R.
Okay.
And so,
Okay.
it's
Yeah.
a great guy. It's kind of like we have our door closed and he has his door closed. And
Yeah.
I'd like that to be when I toured,
Correct.
like it was just open, the door, so, yeah.
Hmm. So remember, to assign oxidation state, we have to use the rules on what's known. So what rules do we have for known elements? We have a rule that governs oxygen, right? We have a rule that governs hydrogen. So we have a known and we have a known, which means we have an
Yeah.
unknown. These are knowns because we have our unknowns. So it's just like a formula, right? We have three variables. I have to give you information about two of them to figure out the third, right?
So.
So it's the same thing here. Mhm. Sure. Good. What's up?
Balance matters, they're both known.
We're getting there. That's part of it, right?
Combination.
Oh, sorry, I see what you're saying. Yeah, so how did you get those numbers there? So, yeah, well, here's our list of rules, right? We have a rule that governs oxygen, so that's a known. We have a rule that governs hydrogen, right? So that's a known. So this is a known, this is a known, that means that's our unknown. Got it? So we have to use our knowns to figure out, right? We don't have a rule about arsenic on here, so it could be a variety of things, right?
So you don't just like use the lines like on the period?
No, right?
Okay.
But you can use that, I'll talk to you guys about that in just a second, right? But
Yeah.
it has a different purpose.
Yeah.
I'll show you guys what it is in just a minute, yeah. No, you got the right idea, right? So, but just pay attention to individual parts here that are getting reduced and oxidized. We'll have to come back with the electrons later, right?
Yeah.
Be careful of that. I disagree with that. Yep. Yeah, so remember this is on an individual basis, right? Each oxygen has a -2, right? So you got the right idea, but be careful just to separate into the individual atoms itself, right? Okay. Let me zoom in here so we can kind of, so we can kind of do one at a time, right? All right, let's do the easy thing first to boost our confidence, right? Always a good strategy for exam taking and in class. Good to impress your neighbors, although you guys aren't sitting next to each other, so you can only impress yourself, I guess, at this point, right? So what's always one of the easiest rules? Well, if you're in your elemental form, your oxidation state, huh?
Sorry.
If you're in your elemental state, right? In your elemental form, your oxidation state always has to be equal to 0, right? We have 7 diatomics, and iodine happens to be one of them, right? So we have iodine in its elemental form, so guess what its oxidation state is? 0, okay? Remember, our assessment is based off of each individual atom itself, okay? Each iodine in there has a 0 charge. Everybody with me on that? Okay? Now we got this other stuff over here, the HASO4, right? Now we have to go to our rules. Well, we went to our rules for the first one there, but now we really have to assess our rules, okay? We've got 3 different atoms in there. And so 2 of those have to be knowns and 1 has to be an unknown. So it's just like any other mathematical formula, right? If I give you an equation with 15 variables, I have to give you information about 14 of those. Got it? And then you can figure out the unknown. Okay? Now you have an equation with 3 variables, the H, the arsenic, and the oxygen. Got it? Do you have information about 2 of those? Yes, you do. Because we have a rule that says what happens with hydrogen. And we have a rule that says what happens with oxygen. Got it? Everybody with me on this? Do we have any rule that says anything about arsenic? No, we do not. Okay? No, we do not. Okay, so what does our rule say about hydrogen? +1, okay? Unless it's a metal hydride. Do we have any metals?
I think so.
Is arsenic a metal?
I don't know.
No. Right? Is oxygen a metal? Right? So do we have to worry about metal hydrides? No. Okay? So we don't have any exceptions. What does it say about oxygen? Each oxygen is -2, with the exception of metal peroxides. Do we have any metals? Do we have any fluorines in here? No, because remember, there's a hierarchy, right? Fluorine will have a -1 if it's bound to an oxygen, which will change things, okay? There's a rule of order as been to part of this also, okay? But very rarely will you see fluorine and oxygen bound to each other. There's a reason for that too, but different arguments for different days. So do we have to worry about any exceptions with any of this stuff? No. So our assumption is each hydrogen is +1, each oxygen is -2. But overall, everything has to add up to be equal to what? Zero, a neutral molecule. Okay, I see we're running out of time here, right? But using that information, okay, using that information, we should get, right, that arsenic here is going to be a, let's change colors, right? We should have a +5 for our arsenic here, okay? We have 3+, right? We have 8-, +3, 8- means +5 from our arsenic there. Everybody with me on that? See if you guys can figure out the rest of this. We'll pick this up on Friday, okay?
What's
Yeah.
minus 5?
Yep. We have -8 from the oxygen, right?
Oh, okay, yeah, sorry.
Is this
Um,
right or is it?
It's okay. What you're getting at there is one of these common issues also, right? Where we mix up minuses and pluses and these kinds of things, right? Very common mistake.
No, you have to have
Yep.
Well, where do you-
the hydrogen.